Okay, let's get started here. So project number 4 is due on Tuesday at class time. We will briefly discuss the one small portion of it that we haven't yet. We'll briefly discuss that a little bit later. Test number 2 is Tuesday, November 13th. I have posted the corresponding folder. The corresponding formulas in our function handout, similar to last time. Posted that there so you can take a look at it before the exam. Are there any questions before we get going here? Okay. So last time we were talking about ways to determine which predictor variables to include in a model. We are actually going through a 4-step model building process, and this is step number 2, which is kind of, you could say, an initial variable screening to try to remove variables that aren't really going to help us to model the response. Try to remove them, and so we can focus on the variables that potentially could help us. And so, in general, we say that we have, let's say, capital P minus 1 predictor variables to choose from. Capital P minus 1 predictor variables. And what we do is we look at a bunch of different, or we look at all possible models that we could have amongst these predictor variables. So we could have models that have 1 predictor variable in it. We could have models that have 2 predictor variables in it, all the way up to P minus 1. And depending upon what P minus 1 is, this could be a large or small number. And so we've looked at 3 different ways to examine all these potential models of interest. R squared, adjusted R squared, and the CP criterion. Today we have 2 more ways, and then we'll get to an example that actually implements them. So we're going to look at the AIC, which stands for Akakie's Information Criterion. This is a very commonly used method to examine models, not just in this class, but also you'll find this in other classes for other types of models as well. And the reason being is because this AIC is used with something called maximum likelihood estimation, or it's used in the context of if you estimate your model through this thing called maximum likelihood estimation. And depending upon your background here, you may or may not have heard of maximum likelihood estimation before. In order to really have a full understanding of what this type of estimation is, you need to take a mathematical statistics course, such as, for example, Stat 883 or Stat 463. So because of that, I am just going to give you kind of a general overall view of what the AIC is, and you're really only responsible for how to implement it. Okay? Again, you're only responsible for how to implement it. Now, so far, our model has looked like this. We say that our Y, our response variable, has a normal distribution. Notice a small change there. And the mean, the expected value of Y is beta 0 plus beta 1 times x1 plus all the way down to beta sub p minus 1 and times x of p minus 1, where notice I'm using a lowercase p there to indicate that this is just some possible model. And the variance we just simply denote as sigma squared. With this setup, if you've had some experience with maximum likelihood estimation, you know then that what we can do is take the product of normal densities, normal distribution densities, over every single observation or data set. We can maximize it, and the values of beta 0, beta 1, down to beta p minus 1 that maximize it are called the maximum likelihood estimates. Again, you're not responsible for that, but I'm just trying to relate this to something that maybe some of you have seen before. In the end, the maximum likelihood estimates that you get will be exactly the same as the least squares estimates that we've been talking about. So that's why we don't focus on maximum likelihood estimation in this course, because this least squares estimation procedure is actually easier. Okay? But with that, though, with the AI with maximum likelihood estimation, people again use this Akakis information criterion. And this is what it looks like. Not responsible for this, but this is what it looks like. It's a -2 times the log of the likelihood function evaluated at the parameter estimates, plus 2 times p, where p, again, this is lowercase p, p represents the number of parameters that are in your model. So p minus 1 predictor variables. Now, if you have experience with likelihood functions, you know that basically with these likelihood functions, the higher the likelihood function is, the more reasonable that model is for the data. So the larger the better. To some respect, kind of like an R-squared. Now let's say if I look at this here, so the larger this value is, the better. Now if I combine this with the log of the likelihood function, do I still have the larger the better? No, we do have larger the better, because this transformation it's a monotone transformation. Put it simply, what that basically means, if you have, look at this. What's the log of 1, log of 2, log of 3? Notice how that's still increasing. If I take 2, so the larger the log likelihood function, the better the model is in essence. If I have 2 times the log likelihood function, is it still the larger the better? Yeah. Now what happens when I take -2 times the likelihood function? Is it still larger the better? No. Now the smaller the better. So in fact, the AIC, the way that we use it is very, very simple. The smaller the AIC, the better your model is. But there's one little problem here with doing just what I have highlighted up there, using what I have highlighted up there. And it's very similar to what we saw with the regular old R-squared. And that is, I can keep on adding parameters to my model, and my likelihood function is still going to increase, just like how it happened with the R-squared. So what do we do? Well, we can adjust this measure. And the way that we adjust this particular measure here is we add a penalty to it. The penalty is a function of the number of parameters in your model. So here's the penalty. And again, we add it because remember, the smaller the AIC, the better the model. So we add 2 times the number of parameters in your model. And that is your AIC. So you can calculate this AIC for all possible models under consideration. The model that is best under this criteria is one that has the smallest AIC. That last sentence I just say, that's what you're responsible for. The smaller, the better. Okay. Now, without getting to the mathematical details here, with this likelihood function, there are going to be parts of it that do not change from one model to the next. So for example, again, if you're familiar with maximum likelihood estimation, you know with the normal distribution, you have that 1 over square root of 2 pi. Well, obviously that's not going to change from one model to the next. So what we can do is remove some of these constants that are going to be exactly the same from one model to the next for exactly the same data set. And our book then uses then for the AIC, so they can actually avoid talking about maximum likelihood estimation altogether, they actually use this particular equation here. These are not equal, but still the smaller the better. If I use the top one or the bottom one, I will still conclude or get to the same model. All the bottom one does, it just removes some constants that are going to be exactly the same from one model to the next. That's it. So it's n times the log of SSE for a particular model of interest. Remember from last time we used that subscript P on SSE to indicate, okay, this is the model that has P parameters in, minus n times the log of n plus 2 times P. So you still see basically that in there. Now there are other types of penalties that could be used. One in particular that our book talks about briefly is that instead one can use a log n times p penalty. This corresponds to what's called Schwarz's Bayesian criterion, or SBC for short. You'll see this, I think, more often refer to outside of this class as the Bayesian information criterion, or the BIC. And in fact, unfortunately, in my notes, I have used BIC a lot of times. And so everywhere you see a BIC in my notes, change it to SBC, unless it's code, because R refers to the refers to the SBC as the BIC. Okay. Again, the smaller the SBC, the better the model. And lastly here, you got to be careful when, let's say, you're computing the AIC in R, and let's say you decided for the fun of it to go compute the AIC in SAS or Stata or some other statistical software package out there. The AIC may not necessarily be exactly the same from one stat package to another. And the reason is it gets up to what the reason is because what I discussed here. And that is there are some constants that are not going to change from one model to the next. And so some software packages will remove this constant, some software packages will remove this constant, some software packages will not remove any constants at all. So you got to be careful and not think that one of the statistical software packages is actually doing something incorrect. It's just what they actually use for the statistic here might be a little bit different from one software package to the next. Okay? Are there any questions about that? Okay. So lastly then, to examine well, which predictive variables are potentially good to include, there's something called the PRESS criterion. And PRESS is a way, or it kind of stands for prediction sums of squares. Now we know that the SSE, sum of squared errors, basically it's represented like this. And in essence, you could say that this examines how good your prediction is with your model. So y is the observed response, y hat's the corresponding predicted value from your model. So you got a residual, you got an error, in other words. You square it and you add them all up. Well, one problem with using this measure is this, that notice that the ith observation, if we just focus on yi minus y hat I, notice that that ith observation was used to actually come up with B0, B1, B2 down to B sub p minus 1. And so you might be thinking, well, yeah, of course, that this model is probably going to do, at least a little bit better by having that actual observation being used to come up with the parameter estimates. So instead, what one might look at alternatively is this, what's called the PRESS prediction error. Y sub I, just like what we have up here, minus now y hat sub I, and that subscript parentheses I is a common way that we use in statistics to indicate how about this measure is calculated where I removed the ith observation from my data set, re-estimated the model based upon this B0 and B1 and so on that I get with this re-estimated model. Now I predict y to come up with this y hat. And so, in essence, then, you might be thinking, okay, well, this might be giving me a better assessment of how good my model is.
The measure of robustness.
Well, you could say it's kind of a little bit more of a more robust measure of your sum of squared errors, yes. And so you might think that this is going to be a better measure of how your model does. Because in order to compute the parameter estimates, that observation wasn't actually involved. If you've heard of the term jackknifing before, this is an example of jackknifing. So just to make sure that this is clear, let's say I want to see how good my model does in predicting the third observation. So what I could do is take what was observed minus what I would predict it to be where I did not have observation number 3 in the data set when I came up with my B0, B1, B2, and so on. And I use the corresponding x's for this third observation to come up with then a y hat. And you could do this then for all observations in your data set and come up with what's called now the press statistic. So how many different models would need to be fit here? We're estimating. N of them, because you have to do that for every single observation. Fortunately, though, you go through some math and show that this press statistic can actually be put into this form here, where notice is exactly the same as what we had before, but I'm using now the model that does include the ith observation to come up with y hat. But I divide by this, 1 minus h sub I squared. H sub I represents the ith, I'm getting tongue-tied here, represents the ith diagonal value from the hat matrix. Okay, well let's remember what the hat matrix is, because this is going to really play an important role starting in chapter 10. So if I write everything in terms of matrices, we have y hat is equal to b times x, right? Where this b vector comes about through taking x prime x inverse x prime y. Oops, I think I got the order. Did I get the order wrong here? Yes, I did. Sorry. Let me do a little erasing. Okay. So we have x times x prime x inverse x prime y. The hat matrix is all the x's. We call that matrix H. Why is it called a hat matrix? Because it puts a hat on y. That's right. So what does the hat matrix look like? Well, I could write it out in this general form. It's an n by n matrix. And there's going to be some numbers on the off diagonal elements. But the diagonal elements, how about we just refer to them as H1, H2 down to Hn? Well, that's where this guy comes from. Okay? We will talk more in chapter 10 about why this works. I prefer to postpone it until chapter 10 because we talk about something called a deleted residual then, and then it will make a little bit more sense why we can do this. So for now, just accept with some faith here that indeed this is how the press statistic can actually be simplified. So indeed, we only need to actually estimate one model. So that's nice. Any questions? Well, how do we choose then between models using this press criterion? Do we want large values of press or small values? Small. Just like with SSE. The smaller this press is, the better the model is. Okay. Now, as I mentioned last time, we're only looking at models that have the first order terms in it. So like x1, x2, x3, we don't have like x2 squared. And in step 3, so we're doing step 2 of the model building process. In step 3, you have an opportunity to consider these transformations, to refine your model. And so this will be more of the subject of chapter 10 when we talk about the step 3. But you got to be careful here, in that you don't want to lose a particular predictor variable that might, let's say, have actually a quadratic effect on the response. But because of the type of quadratic effect, maybe it just doesn't show up in a linear form as well. So if maybe based upon your knowledge of a data set, you know that some variable, let's call it x1. Let's say that x1, that you think it might have like a quadratic effect or some other kind of transformation, But even though it doesn't show up to be in any of the good models that we've developed through using these measures, you should still consider models that has that variable in it that maybe does not necessarily show up immediately as being important. So please be aware of that. And this is often, a difficult aspect of choosing which variables to include in your model. Because this depends upon maybe your knowledge of a particular problem of interest, and you may or may not know that, beforehand I think maybe a minutes per game squared is indeed probably going to be important. So, it's a difficult aspect. Let's see. Okay, so Fox and Weisberg, they talk about how to implement this. I have my own way to implement these measures. Okay, so let's go to the NBA guard data set again. If you remember, we have 5 possible predictor variables, and what we like to be able to do is, remove those that we don't think could help us in the end to predict the response of PPM. So what we're going to do here is, first of all, estimate a model that has all of our predictor variables in it. We're going to put the results from this model fit into mod.fit. I'm going to summarize the fit, and then I'm also going to pull out the MSE as we have done before. Okay. Now, to look at all these particular measures of how good a model is, what I've done is wrote a function that will hopefully simplify your lives, because it will calculate all the measures for you automatically. Now, you are still responsible to understand, how this function, the details inside the function. But what I recommend for you to do is simply use this function when we're doing some of this kind of stuff. Okay, so make your life easier. So the function, I simply call it fit.stat, and there's 3 parts or 3 items that you have to pass into it. The model formula for what you're evaluating, so maybe PPM tilde age plus FGP, for example. The actual data set name, and then the MSE that you get from the model that has all of your predictor variables in it. That's why I did this part right here. Okay? Then what do we do next? Well, I estimate the model of interest, I summarize the model, I find my sample size, and now I compute these measures that we've been talking about. First of all, to compute the AIC, there's a function R called AIC. Notice it's all in caps. I simply say object equal mod.fit from above, and then k equal 2. This corresponds to that penalty that we saw, which was 2 times p. To do the SBC, exactly the same, but now, of course, the penalty is log n times p. So I put a log n there. I can calculate SSE as well through using means that we've done in the past, so I'm not going to go through that code. Number of parameters that are being estimated in my model. Here's my CP. SSE divided by the MSE from all the predictor variables minus n minus 2 times p. Remember, with the CP, we are looking for models that have a value that is close to p, your number of parameters. Here's how I calculate the press statistic. Not much new in how I actually would do this. I take the sum of my residual squared divided by 1 minus, this is my h sub I. This is a new function we have seen before called lm.influence, linear model influence. What we're going to see in Chapter 10 is that this HAP matrix plays an important role to determine if a particular observation is influential to what the B's are for our model. So we'll talk more about this function later. For now, we'll just use it. And notice I squared as well. And then at the end, I return a data frame that simply has all my measures that I'm interested in looking at. Okay? So that's the function. So let's actually use it. Let's see. So I'm going to read in my data, get my fit.stat function into R, get my overall MSE. Go ahead and run all the way down to there. So let's look at implementing it. So I say fit.stat, and I'm interested in a model that has 4 predictor variables. So MPG, height, free throw percentage, and field goal percentage, and I'm leaving age out. My data is in the NBA data frame. Here's my overall MSE. And let me just run this portion right here. So
MSC from the full model.
full model, or complete model, the model that has all predictor variables. And this is what I get back. So it has an R squared of 0.28, adjusted R squared of 0.25, and you can see the other statistics as well. How about I put the results into an object called mod 4.1. So 4 variables, the first model that has 4 variables. And we can also do the same thing for another model that has 4 predictor variables as well, but now field goal percentage is left out. And it's going to be put in mod 4.2, and there we go. Okay, now if I want to compare model 1 to model 2, which model do you think is better? 1 has a higher R squared, has a higher adjusted R squared. AIC is smaller, SBC is smaller, the press is smaller. Look at the CP. In this particular case, we'd be comparing it to the value of 5, because there are 5 parameters being estimated, so the 4 predictor variables, and then the intercept. None of them are exactly equal to 5, but which one's closer? Well, model 1's CP. So we can now repeat this process for all possible 4 predictor variable models. That's what I do here. And how about we use, I think we've seen this function before, rbind, which stands for row combine. Take mod 4.1, put mod 4.2 right below it, put mod 4.3 right below it. So I'm combining these data frames by rows. Let's go ahead and do that. And there's the 5 models. So of these models, which one's best? The third one. And while this will not always happen, but using all these criteria, they all agree. They all agree that the third one is the best. Now, it might be nice if we could maybe, let's say, sort this data frame that we just produced so that we always have the best one up top, the second best one second, and so on. So how can we do that? Well, the first thing I'm going to do is actually put all this stuff together with model number labels. So, we have models 1 through 5. So how about if I do 1:5 to get 1, 2, 3, 4, 5. And then using the cbind function, what that's going to do is have a column here, model 1 through 5, and then it's going to put the stuff that resulted from the rbind right next to it in separate columns. I put then an object called var4 for 4 variables. Okay. And now what I want to do is sort. Here's how to do it. First of all, I am going to look at the ordering by the R squared. So I'm just going to use R squared. I could have picked some of the other measures too. I'm just going to pick R squared here. And I'm going to look at the order amongst all the R squares in terms of, notice how the third row here, of course, had the largest R squared. And notice how the order is represented by 5. The model that had the smallest R squared, oops, a second. So this is telling me that the okay, I'm sorry. Yeah, I was misreading. So the row 2 had the smallest r squared. So model 2 had the smallest r squared. And notice how this is actually listed first. Okay? So model 2 had the smallest r squared. And so it's listing basically row 2 first when I do the order function. Okay? Yeah, it obviously can be confusing, because I was confused at first. REV stands for reverse, because what I like to show is actually the largest r squared first, rather than small. So let's reverse those numbers. So notice how 3 is listed first. And now, that those numbers then tell me, well, which rows to display. So I say var4 bracket, I want row 3 first, based upon what's given by this, and so on. And so now everything's properly sorted. And just to make it look nicer, I could use a rounding of 2 decimal places as well. And so that's how you could do it. Any questions? Okay. Now overall, I think I may have said this before. Overall here, when we're looking at 4 variables, I'm sorry, 5 variables total, how many 4 possible variable models are there? And this just then comes about through using a combination. 5 choose 4. So there are 5 possible ones. In general, you can see, how you could use a combination to figure out, well, how many actual models are there? Let's look at all the 3 variable models. These have been properly sorted as well. So model 3 amongst all the 3 variable models is the best there. And what does model 3 correspond to? It corresponds to the model that has MPG, height, and field goal percentage in it. For all the 2 variable models, the best one is model 6. Again, which one's model 6? You just have to look at everything written out, height and field goal percentage, and you can keep on going, look at 1 variable model as well. So it might be nice then that you were looking at tons of different models. How about we use some graphs to help us make sense of all this, and so that maybe we can choose amongst the different number of variables which model is the best. And so what one could do is a plot similar to this. I did this just in terms of r squared, but you should do this in terms of the other measures too. And what I did here, we'll look at how I created this plot shortly. On the x-axis, I have the number of variables, y-axis, the actual r squared measured. And so we can see that, if you remember when we were looking at the r squared, basically we're looking to see where does this start to level off. And that will kind of correspond to which model is the best. Because remember, we keep on adding variables to our model, and still get a higher r squared. And it appears to level off maybe here or here. Where what's being plotted there as the plotting point is the model number. So remember how model 3 was the best amongst the 4 variable models. Model 3, that number, happened to also be the best amongst the 3 variable models too. Well, how do I construct a plot like this? Well, the first thing I can do, remove some code here temporarily. The first thing I'm going to do is I want to plot on my y-axis the r squares. On my x-axis, what I like to do is plot some label that represents the number of variables that are in it. And so what I'm going to do is I'm going to grab for all my 1 variable models, so that's what var1 represents. I'm going to grab out all those r squares and plot that versus the number 1, because This represents one variable models.
Why not put one with the better?
Well, it just helps you evaluate all the models at the same time. There might be particular reasons why you don't necessarily always choose the one with the highest R squared. Maybe without getting on the reasons, there are sometimes reasons why you want to do that. I'm going to control the y-axis limits to be between 0 and 1 because, of course, R squares are between 0 and 1. X-axis limits, well, what I like to do is actually plot it for one variable models, two variable models, all the way up to 5 variable models. And let me go ahead and produce this plot. And so you can see the first portion of the plot that was on the bottom of page 915. Well, how about I also plot, well, which model numbers are these actually? And so what I can do is I can use the text function to actually put the model numbers on the plot. So I have the exact same X, exact same Y, but now I use labels. I pull out the model number from var1. And this is what we get. Obviously, it's a little bit harder to read because we have those circular plotting points there. Well, really, we don't need those circular plotting points. All we want is the model numbers plotted. So instead, and then this is what the code represents in the notes, I'm going to add the following argument, type equal n. We may have seen this before. Type equal n means don't actually do any plotting points. So if I do that to my plot function, notice I don't have any plotting points now, so that when I do use the text function, all I see is the corresponding numbers. And I continue to do that for the 2 variable, 3 variable, 4 variable, and 5 variable models as well. And there's our plot. Okay, so it's a little work, but it's a helpful summary of what's going on. Okay, are there any questions? So overall, based upon what we've been doing here, here are the actual models that look to be good. We found a 3-variable model that had MPG, height, and field goal percentage. We found a 4-variable model that had MPG, height, field goal percentage, and age. And also, if you actually look at the plots, you'll notice the MPG, or the R squared for MPG, height, free throw percentage, field goal percentage is just a little bit lower. So these are 3, you can say, candidate models to consider further in your step number 3. The largest R squared, adjusted R squared overall, was MPG, height, field goal percentage, and age. If you look at all of them. Some of them are kind of similar, so you might want to consider those as well, which kind of corresponds to what was up here. Okay, so what would you do next once you've done this? Well, you move on to the step 3, where you refine your model. Look, for example, for interaction terms. What I would typically do is pick the model that I think is the best overall, which I would probably choose this one, but still have in the back of my mind that there were some other models that weren't too bad either. And so that if this particular model starts developing problems that I find in step number 3, I can always go back to some of these other models and see if I can refine those models and see if I get something better. Okay. So let's briefly talk about the project then. So problem number 1A here basically has you do the stuff that we just did with respect to the cheese data. So what you need for part I here, so for the model that has, or for considering the situation where you have 3 different predictor variables, and compare that to the model that has just 2 predictor variables. What I'd like you to do is simply calculate these adjusted R squared, CP, EIC, and press measures. You can calculate R squared too if you want. I just left it off. Then tell me which model is better based upon these criteria. And then finally, discuss how your results here coincide with a t-test for acetic acid that we did in project number 3. So you found in project number 3 that acetic acid, given the other variables were in the model, acetic acid was non-significant. Well, how does this finding correspond to what you're finding with all these measures of how good the model fits? Simply, that's problem 1A. Not too difficult, but just as a helpful tool to get you some experience with calculating these measures, and also to relate these measures to something that you should be familiar with already, a t-test result. Okay, so section 9.4 then. Oh, that's not good. Okay. Excuse me. Automatic search procedures for model selection. So, there's going to be times where you have so many predictive variables, it's going to be tough to look at every single model like what we just got done doing here. So, there are other things that can be done to help search through the models to figure out which one is the best. You do not necessarily end up actually estimating every single possible model then in this situation. And so what we're going to talk about here, first of all, is something called the best subsets algorithm. What this basically does, it's an algorithm that goes through your models, not necessarily fitting all of them, but goes through all possible, let's say, stated models, excuse me, and then just simply tries to find which is the best. And let's go ahead and jump into an example that examines this in more detail. This example uses functions from the CAR package, which we have done before, and also something called the LEAPS package. Inside the LEAPS package, there is a function called reg subsets. This is how the syntax works. With respect to the MBA GARD data set, you put in, you can say, your complete model that has all your predictor variables. Specify your data set. Method equals exhaustive, which basically just means you're interested in all possible combinations of the variables of interest. N best equal 4. What that's going to correspond to is going to find the 4 best models for 1 predictor variable models, for 2 predictor variable models, for 3 predictor variables. So 4 best models for each number of possible predictor variables that you could have. You could change that to n best equal 3, 2, if you wanted to. I just chose 4 just to demonstrate it.
So it will be 4 per each number.
4 per.
Not in total.
Yeah, not in total. And then we can summarize the results. And this additional argument here basically puts the results in a matrix-like structure, which is somewhat helpful, as you will see. So this is what we get. The main thing for us to focus on is this here. This is the matrix. This is what was actually produced in the end by using that argument. Okay. So what we see here are groups of 4 possible models based upon the number of variables. And what this procedure says is that the model that has just field goal percentage in it amongst all 1 predictor variable models is the best. The one that's second best is the one that has MPG in it. Amongst 2 variable models, the model that's best is the one that has height and field goal percentage in it. And you can see this throughout. Now, why don't you see 4 possible models here? Well, there's only 1 possible model that has all the predictor variables in it. Now, unfortunately, if you notice here, it doesn't, say, well, how's it choosing which model is best? It's not even giving you any numerical summary measures at all. So that's one reason I guess I don't necessarily like this as well. But, and this is now page 919, my discussion here. I guess I've never been 100% confident through looking at the code for this function and looking at the help. Never been 100% confident of knowing exactly how it's choosing one model is the best. I'm pretty sure, but not 100% sure, that it's actually organizing by CP. So I mean, it's kind of disappointing not necessarily knowing exactly 100% sure what's being done, but I'm pretty sure it's the CP that's being used here. You can get some other additional information out from this function, or from running it. So I remember I have my results from that summary part saved in, just make sure, select.sum. This was on page 917. I said select.sum gets summary. And you can actually now pull out R squares, adjusted R squares, the CP. Notice it calls it the BIC, but that's our SBC. You can pull those out and look at them, and they'll give you a list of all of them, and you can actually then merge them in a data frame if you wanted to with the results from that little matrix-like structure that we saw as well, so that you could actually see the numerical summary measures if you wanted to. So at least you could do that. It's just unfortunate they don't organize the output like that. I do recommend avoiding doing n best equal 1. You might be thinking, geez, that's simple. Let's just look at the best of each number of predictor variables. And the reason being is because some of these summary measures, could come up with different best models. And so that's why I always would look at more than one. Let's look at some plots that help summarize the results. Well, the plot function can actually be used with the results from the reg subsets function. And it produces a plot like this. How do you interpret it? I don't know. There's no documentation. It doesn't really say exactly how to do it. But what we can do is this instead. In the car package, remember that corresponds to our book by Fox and Weisberg. Let me find my place in the notes here. They have constructed their own function that is, or their own function that produces a better plot, and so that's what we will focus on. And in fact, in their book, they will say that their plot is a lot easier to interpret than the one from the Leafs package, and I agree. So if I say subsets, so again, this is in the car package, subsets object equals select.var, so the results from this reg subsets function. My statistic of interest, I just chose the SBC here, or what this function will call the BIC. Put legend equal true to give you some graphical summary of what's being plotted. And then cex.subsets just corresponds to the font size, so 75% the default. And this is the plot that we get. Let me blow this up. So we have SBC here. We have number of variables on the x-axis. And notice this is what the legend gives you. And what we have here is basically the models being plotted by their SBC. So for example, well, let me ask you, which model is the best according to the SBC? MPG, height, and field goal percentage. Because remember, smaller the SBC, the better the model. And so this is, kind of like the plot that I had drawn earlier with the R squares, but this is just more of an automated way to get it done. So that's nice. Yes.
Are there any loans and products that you don't have no other lines for each other?
I'm sorry, could you speak up, please?
So on plot, there's several models that are lying over each other in one way of plot.
I don't think that there is. And obviously that would be a problem. But remember, you still always have access to the numerical values like I showed you, so you could always go back if you were not for sure, through the overlay, which is which. Just out of curiosity now, let's take a look at the help for subsets. At least here, I don't see a particular argument that will prevent the overlapping. What can often be done is to, again, make this font size smaller too. That can help, so that you can make sense of it.
You set grids and maybe instead have it here and it 5 and 0 and
You mean change the y-axis?
yeah.
You perhaps could do that too. If you could, let's say, focus in narrower, you would lose some stuff being shown in the plot. But I would imagine that you could focus in, and that would help blow it up, and maybe you could see it better. Okay. So just a quick note here. Again, there's a number of places where I put BIC instead of SBC. So, sorry. So we can also do some additional plots for the other measures too. So that's why I decided to do here, where I decided to make basically a grid of two rows of plots, 2 columns of plots. I do the R squared, the adjusted R squared, CP, and SBC as well. And this is what I get. I left off the legend just because we already had a legend on another plot. So we can see, for example, with the, let's see. So we had already looked at this particular plot, and we said that the MPG height and field goal percentage was the best. Let's take another one. Let's do adjusted R squared. That concludes MPG height, field goal percentage, and age is best. Where, of course, we're looking at the highest value. Note that there's a small typo here. We need to compare CP to P, not I have 6 there.
What's the meaning of CP below the number of
Yeah, I mean it can drop below, but that's mainly just due to sampling variation. It shouldn't be too much lower than P.
But in this case, what would be the best? The one that's closer to 5 or the lowest?
The one that's the lowest. But I mean, you can still think of it in terms of what the CP means. Any model that is close to P would be good. Okay. So page 924 now. So we're still talking about automated ways to choose between the variables so that you don't necessarily need to actually estimate every single possible model. And we're going to look at 3 different procedures that basically kind of step you through a particular process to do. The first one's called forward selection. And the way that this begins is with a model that has no predictor variables in it at all. And we look, which one predictor variable is the best, let's say, to include in the model. So fit a regression, simple linear regression model for each predictor variable. Pick the best model. We'll talk about what I mean by best, but you can imagine, I guess we can talk about now. How do we judge best? Well, you might choose the model that has the lowest AIC, for example, or the highest R squared. Next, starting with model number 1, add another predictor variable to it. So if model number 1 chose x1, or I'm sorry, step 1 chose x1, look at a model now that has x1, x2 in it, estimate. Look at a model that has x1, x3 in it, estimate. And then from there, choose which of these two variable predictor models are the best. And you keep on going through the same process of adding adding predictor variables to the model. So in other words, you're kind of going forward in how you're selecting variables. You're adding one at a time. You keep on doing that until you get to a point where you're not really improving the model at all. I'll explain what I mean by not improving the model at all coming up. Okay. So let's go through a little quick example. Let's consider a situation that I have variables x1, x2, and x3. And what I do for step 1, I estimate a model that has x1, I estimate a model that has x2 in it, and I estimate a model that has x3 in it. And I need to decide, well, which of these models is best? You know, again, we could look at an R-squared, we could look at an AIC, we could look at a CP, we could look at all the other measures. Here's another way that we could do it. How about we look at a t-test p-value? So the regular old p-value that you would have in your output from using the LM function and then summarizing it. And suppose that this p-value for x1 is, let's say, maybe 0.01. Oh, that's saying that perhaps that this is a very good, very important variable. Maybe x2 it's 0.2. Maybe for x3 it's 0.5. Again, this is from 3 separate models. So if you had to choose which of the predictive variables is best, which would it be? Seems like x1, that would be a reasonable conclusion. So I choose x1. Then step 2. Now I want to see, well, maybe I should add x2 to the model. Maybe I should add x3. So I'm going to use this little notation here to emphasize that given x1's already in the model, let's look at, should I add x2? Should I add x3? Again, you can look at the AIC, you can look at R-squared, but let's be consistent here and look at a t-test. And perhaps I get a p-value of now 0.0, oh, let's do 0.03, maybe now 0.4. Do you think I should add any predictor variables? Yeah, maybe x2. You know, it has a relatively low p-value, so, and x3 does not, so why don't we add that? And so now step number 3, I look at, well, can I add x3 to a model that has already x1 and x2 in it? I get the t-test p-value, and let's say it's 0.45. What do you think? Do you think x3 is worthwhile to include in the model? No. So I stop. So my model then has just x1 and x2 from using this forward selection procedure. Now let me emphasize that this is not a perfect procedure. This is just one way to proceed when you have a lot of variables to choose from. I'll have a discussion about some problems that this procedure has. I'll have a discussion about that later. But it seems like it's a reasonable approach. We're using hypothesis tests to help us determine which variables are important. What happens if you would have a qualitative variable under consideration? Again, you would need to consider that qualitative variable altogether and do one test for that qualitative variable. You would not do individual tests for the indicator variables. But what test would you use to assess the importance of the qualitative variable? Would you use a t-test? You would use a partial f-test. Okay, so you use a partial f-test to make the same decision. So you might be wondering, this is on page 925 now, you might be wondering, well, how low does my p-value have to be in order to say, yes, I should add that variable to the model? Well, typically we are very conservative in this particular stage of the model building process. We don't want to maybe lose any predictive variable that could potentially be more important down the road. So because of that, a general recommendation that our book gives is to use a level of significance of 0.15. So higher than what you would normally if you were to use a strict type 1 error rate, let's say, to make a decision of reject or don't reject HO. There will be times later in step 3 where you can say, okay, that variable is not that important in the end, so why don't we just go ahead and remove it. We kept it in there for now just to see if it would pop up maybe to be more important later on. Maybe it doesn't, so let's go ahead and just remove it. In step 3, you have opportunity to do that. Okay. So you look at the places where you replace the BIC with the SBC. Again, you could use AIC as the same way, but of course, you're looking for the lowest AIC in this step forward process. Let's take a look at an example of implementing this with the NBA GUARD data set. So we're going to jump ahead to page 928. There's an easy way to do this in R when you're using the AIC or SBC. So first thing that you need to do is estimate a model where you would start the process of the forward selection. So I'm going to create an object called mod.fit.org, LM function formula equal ppm tilde 1. I think we've looked at this before. When I just put a 1 there instead of any predictor variables, that tells R just estimate a model that has the intercept only. So all you're going to get is B0. On your own, after class, you can verify that indeed that this is what actually happened. Then, use the function called step in R, where you put in for the object argument where to start, direction equal forward, scope is, well, I don't want to get any lower than this model in terms of the number of terms in my model or anything higher than another particular model. In other words, we say scope equal list. Here's, let's say, my lowest model in terms of the least number of predictor variables. And my highest model has all the predictor variables. K equal 2 corresponds to, again, that penalty with the AIC. That 2 times P, K is the 2. I put the results into step.4 so I can summarize it later. By default, this is the output that you get immediately to your screen. First of all, R looks at the model that has no predictor variables in it and calculates its AIC, negative 451.58. Then it looks, what happens if I add field goal percentage? What happens if I add minutes per game? In other words, having simple linear regression models. And it actually orders it from smallest to largest for the AIC. Again, the better model corresponds to smaller AIC. So what that says is that field goal percentage, let's go ahead and add that to the model first in this forward selection process. Notice here, it even puts an entry for none, meaning if you don't do anything at all, this is your AIC. And look what happens if you add H to the model. The model actually gets worse using this criterion than if you wouldn't do anything at all. So now my AIC is negative 468.53, where I have field goal percentage in my model. Should I add any other variables? So, given field goal percentage in the model, let's look at height. Let's look at minutes per game. Let's look at age. Let's look at free throw percentage. And we see that height lowers my AIC the most. So, let's add height to the model. So now I have a model that has field goal percentage and height in it. I do the same process, look at minutes per game, age, and free throw percentage. We see that only minutes per game lowers the AIC. So I add minutes per game to the model. So here's my model. Now, with minutes per game in the model, in addition to height and field goal percentage, my AIC is actually lowered when I include age. So I add age to the model. And then lastly, I look, does free throw percentage help me? No, it actually increases AIC. So then I stop. So this found that field goal percentage, height, minutes per game, and age was the best model using this particular criterion. And this actually corresponded to, let's see, when we use the adjusted R-squared, you might want to put a page reference here, 9.16. When we use the adjusted R-squared, we got exactly the same model when we were looking at all possible models. So what's inside of this step.4? Well, there's a number of things. If I were just to say, so this is where I put the results from the step function. There's a number of things in there. If I just simply say step.4, I get an estimate of my final model. One component that's inside of there is called ANOVA, because it's kind of summarizing, various, you can say variance measures. Because if you notice here, notice how sum of the squares was also given too. I just didn't look at it. And so what this does, it gives you a history of the process. Okay. Any questions? Let's jump ahead again to page 932. Yeah.
So the model that's suggested by this process ends up having a coefficient on age that's not statistically significant?
Yeah. Yeah.
So then in your interpretation, do you then conclude that it's not significant?
Well, that's the problem with these model building approaches. You will not necessarily get the same model. I know I would personally have a problem with including a variable that's in your model that's not significant. But again, it depends upon what you mean by significant. What are you using alpha 0.1, 0.01, and so on. And I would expect, and I guess I don't remember this for a fact, I would expect age would have a marginally significant p-value. Right. But then you have to think too in terms of if you do have a marginally significant variable in your model, is that really affecting your predictions a whole lot? Because it's actually marginally significant. Or if it's even non-significant, is it really affecting things much? Probably not going to affect things too much. Well, what would happen if I wanted to do this same process now using hypothesis tests, like I had demonstrated through that simple three-variable example? Well, unfortunately, there's not a nice little function in R that does this for you. So you kind of have to do it, you can say, by hand to some respect. To help you do this, I've actually created a function here that will automatically summarize the results for you and to give out the p-value of interest. So this is what the function looks like. It's called test.var. You simply structure your test so you have an HO model and you have an HA model. So you can test one variable at a time. And then pass in your data. I do a partial F test. And I return the result. The reason why I use the ANOVA function here to do this partial F test is because, remember, a t-test and an overall F test are special cases. So that's why I do this here. And then so to start the forward selection process, what do? I start with, remember I'm starting with a model that has nothing in it, no predictive variables. I want to see which one predictive variable should I add first. So I create an object called MPG that gets the results from test.var, where my HO model has no predictive variables in it. My HA model has MPG in it. I put the results, which will be a p-value, into MPG. I do the same thing for height, free throw percentage, field goal percentage, and age. So let me just show you indeed that that's what happens. So if I look at just MPG itself, there's the p-value. So it's significant. It's a low p-value, indicating that MPG is important. And to help summarize everything, I put everything into a data frame. And based upon this, which of the variables do you think we should add first? What's that? Not MPG. FGP, field goal percentage, because notice it has the smallest p-value overall. What would happen if you had MPG also listed as 0 and FGP listed as 0? Would you say, oh, can't do it? Would you say that?
Add both.
You want to add both. You still want to add just one variable at a time.
We tried both routes.
You could try both routes, yes. Another thing you could do, notice in my code here, I round to 4 decimal places. Change the code. Go to 5, go to 6. Okay? If both MPG and field goal percentage end up being in your model, well, great. If, let's say, only one of them ends up being in your model, then this is definitely when you want to try the approach where you want to try, try FGP first, see where that gets you. Try MPG, see where that gets you. Because remember, there are cases where you can have multicollinearity problems, where maybe both these variables measure the same thing, they just both happen to be highly significant, and you don't want to have variables that are both measuring the same thing in your model. Okay. So we add FGP. Now, given that FGP is in the model, let's look at the other variables too. So we look at MPG. We look at adding height. We look at adding free throw percentage. We look at adding age. And we use this test.var function to help us do that. Okay. Which variable should I add to the model next? Height. Okay, because it has the smallest p-value. And in case I didn't really emphasize this before, the reason why we do this is because this is basically saying that this variable is the most important, the most significant, you could say. There's the most evidence that this is the most important of the remaining variables. So we add height to the model. So notice what my HO model is. And then I look at MPG, free throw percentage, age. What should I add next? MPG. So we add that. Let's look at free throw percentage and age. Well, age is a little marginally significant. Well, we just add it for now. We could, remove it later on if needed. So we add that. And then lastly, we're looking, should we add free throw percentage? What do you think? No. Large p. Okay. So notice we end up with the same model as we did with the AIC. That will not always happen, but that's what happened here. Okay. Are there any questions? Okay, that's it for today then.